So let us do so the last thing we saw in the previous lecture was this idea of density evolution for soft message passing, and let me just quickly summarize that. Remember, this is for BPSK AWGN, right, and the AWGN is parameterized by the channel noise sigma squared. Okay. So what? Okay, you start with the first iteration where V1 is distributed as normal, mean 2 by sigma square, variance 4 by sigma square. Okay. So this is the PDF of the channel LLR. Okay, this is the PDF of the channel LLR. And how do you find the PDF of V2? It is some formula, and it is basically FV1 convolved with this function lambda and then this function rho of f. Let me write VL in terms of L minus 1. Okay, so that is better. L minus 1, you run this from L equals to 3 onwards. Okay. So remember, how does this PDF look? Okay, this mean 2 by sigma square and variance 4 by sigma square, it will look something like this. Okay, well, maybe not quite like this. Okay, so the PDF will look like this, right? What is the probability of error in this PDF? In this picture, this area, right? This is the probability of error. Yeah, you can even do with Q, it will be Q of 1 by sigma. It has to be Q of 1 by sigma. Just because I multiplied by 2 by sigma square, suddenly probability of error cannot be different. It has to be Q of 1 by sigma. Okay. So that will be the probability of error. Okay. So in general also, after L iterations, what is the probability of error corresponding to a particular PDF FVL? Okay. So that we will define as PL. PL is the probability of error. Okay, remember, all my messages are supposed to be log likelihood ratios for the corresponding bits. Okay, on an edge you have a bit node on one side. Every message is an LLR for that bit, and I know that bit is already 0, right? I am restricting myself to the all 0 code word. So if I have an error, that bit must go to 1, which means the message must be negative. Okay, right? If my bit is 0 and the symbol is +1, my message has to be positive for no error and negative for error. That's how you said this area was the probability of error, right? So probability of error for the Lth iteration is simply probability that VL is less than 0. Okay. So the integration, I mean the area under the curve on the left side, it's a probability of error. Okay. So as you do iterations, okay, this is basically FV1, right? V1, am I right? What do you expect FV2 to look like? Hopefully it will get compressed on the left side, and the peak will maybe shift to the right. Okay, and as you keep iterating more and more, what do you expect your PDFs to look? The probability of error hopefully is lesser, and then the peak is shifting to the right continuously. Okay. Eventually, if for L tending to infinity you were to assume you were to get 0 probability of error, then what should have happened? There should be nothing on the negative side. Okay. It should have totally gone off to the right. Okay. So that's the idea. Okay. So based on this definition of probability of error, you can define a threshold. Okay, sigma star, which is maximum sigma such that P infinity is 0. Okay. Okay. So, this is the threshold that I have plotted here. Okay, this threshold line some 1.1 dB for 3,6 regular codes, that is the 1.1 dB. Okay. Remember, I will get a sigma star, I can always convert a sigma star into an EB over N naught. Okay, 1 by 2 R sigma square is the formula, right. So, R is equal to half here, plug it in, you will get a EB over N naught of 1.1 dB or so. Okay, so that is the threshold that I have plotted here. Okay, so how will you compute this threshold? You really need this density evolution formula. Okay, so you start with the low enough sigma. Okay, let us much lower, so that V1 is a PDF which is mostly to the right, and then you do a few iterations of a density evolution, you are going to get 0 probability of error, and then what do? Keep increasing your sigma slowly till you get to a point where the PDF is not really continuing to move to the right, it gets stuck somewhere. Okay, if the PDF gets stuck somewhere, then it is not going to move to the right, and you are going to get a non-zero probability of error. Okay, so that is what you look for in density evolution. Okay, so it is not as simple as BSC anymore, where you could just see whether the number is tending to 0 or not. Okay, you have to actually track an entire function and see if it has any area on the negative side. Okay, that is what you have to see. It is a little bit more complicated, but it can be done. I mean, it's you can do it with good precision, and you will get your answer. Okay. Is it okay? I mean, it is also, hopefully it is also clear to you how the iteration is starting, right. If you put L equals 2, you only need FV1, okay, and FV1 you know already. So, it starts and it proceeds like that. Okay. So, maybe I have some pictures, I do not know, maybe I have, maybe I do not, I am not very sure. So here are some pictures. So, these are actually some density evolutions that I did, for a 3,6 regular code. Okay, for sigma equals 0.6, that is shown on the left side, and sigma equals 0.9, that is shown on the right side. Okay, so on the left side you are seeing, so the blue is the original, the first blue that you see on the left side, that is the first LLR PDF that you start with. Okay, that is the PDF of the channel LLR. Okay, I do one iteration, so this is okay. I do not think I can write on top of this, right? But this will be like a 56-page document. Oh, I can copy and paste, right? Okay, so let me just do this. Okay, so that is better. So, this is the, let me do this and then maybe zoom this. Okay, so this is first iteration, this is second iteration, this is third iteration, this is fourth iteration, fifth iteration. So, you can see what is happening, right. So, initially you have, remember this is my y axis. Okay, so initially you have quite a bit of area to the left of the y axis. Okay, and then after you do first iteration, it is shifted to the right and it is compressed on the left side. Okay, then the third iteration is even further down. Okay, and finally by the fourth or fifth iteration you are saying it is pretty much 0. Okay, so this happens at sigma as 0.6. Okay, so this is once again for the 3,6 regular code. Okay, so that is rate half. So in terms of, I think if you think in terms of you can't quite see the resolution here, but think in terms of resolution, minus 25 to 25 is good enough. Okay, so you are thinking, I mean, so you have to think about a lot of things when you numerically implement this, right. I am looking at the PDF of some random variable. Okay, what should be the range that I should keep track of? Okay, I cannot keep track of an infinite range, it has to be some finite length only. Okay, so here I am keeping track only between -25 and +25, and that seems to be good enough. Okay, so it's a good number to remember. -25 to 25 is a good range of LLR. Okay, LLR being 25 is a large number. I mean, that's pretty much enough. Okay, and then resolution also matters, right. -25 to 25, I can't store a real valued function. I mean, I can't real number function and all I can't store. Okay, I have to take resolution. So this might have been like 10 bits or so. Okay, I might have divided this into about 1000 intervals and binned everything in the interval. Okay, some resolution you have to take, finite resolution. It looks quite. I mean, you can see the steps maybe a little bit. If you zoom in, maybe when it goes up, you can see some minor thing, but the resolution is quite big. Okay, quite good enough. So it's quite small. Okay, and this is sigma 0.6, and then the next thing, sigma 0.9. Let me do the same thing. Okay. So you can see the probability of error, I think that is 10 power minus 3. Okay. So if you are wondering about the y axis, that is 10 power minus 3, it is not 10 power minus 8 or something. Okay. So it is quite big. So when your noise is very large, your decoder is not going to give you 0 probability of error. Okay. So it is beyond the threshold. Okay. So when the noise has gone above the threshold, it is not going to give you 0 probability of error, and that you can see in this picture. That is your y axis. And you see, as you keep doing more and more iteration, 1, 2, so on till like 5th iteration, you have pretty much, you have reached like a fixed point of a iteration. Okay, you take a function, you go through the iteration, you get the same function back. You keep on doing it, you hit a fixed point. Okay, you are not going to improve beyond that. Okay, and that gives you a finite probability of error. Okay, so based on these two runs, you can know that sigma star lies between 0.6 and 0.9 for rate half codes. Okay, the accurate thing can be found now by repeating this step over and over again. Okay, now you say, okay, maybe it is 0.8, 0.7, 0.75, the actual number will come based on that. Okay, so to find sigma star, you have to repeatedly run density evolution for multiple iterations several times. Okay, only then you will get sigma star. Okay, and you will have to compute several sigma stars when you are trying to optimize the degree distribution. Okay, so to have a very good efficient density evolution is very important. Okay, and that's useful when you design LDPC codes. Okay, I think that's probably the last slide that's interesting in this. So this is a picture for something. And then some thresholds. Okay, so these are nice things to see. Okay, here are some thresholds for rate half codes. The capacity is 0.979. Okay, so this is BPSK AWGN. So capacity sigma star is 0.979. What do I mean by capacity again? Okay, what is capacity again? Okay, so when I say capacity is 0.979, what does it mean? It means for any sigma less than 0.979, I can have a rate half code for long enough block length that gives me arbitrarily low probability of error. Okay, 10 power minus 6, whatever. So that is what capacity means. Okay, now threshold, what does threshold mean? For 3,6 regular codes, for any sigma less than 0.88, if I go to a long enough block length, my probability of error will go down to 0. That is what it means. So the gap between threshold and capacity is non-zero. Okay, 0.88 and 0.979. You have not come up to capacity. You can do better designs, but you are stuck at 0.88. That is because of regular 3,6. Okay, if you go to 4,8, what happens? You get 0.83, which is worse than 0.88. Okay, all right. So in the Gallagher A decoder, we saw that 4,8 was better than 3,6. In BPSK AWGN soft message passing decoding, 3,6 is the best rate half regular code. Okay, 4,8 is poorer, 5,10 is even poorer, As you keep going further and further, it will be even worse and worse. Okay. So, based on just regular codes, if you were to ask what is the best rate half code, it is going to be 3, 6. Okay. By the way, make sure you mug up all these numbers, because some number like this might, no, I will not ask you questions based on these numbers. Don't get scared. I immediately see people in this. Okay. So that is that. Okay. So now let us this is all some slides on irregular codes. Okay. Okay. So how do you get to capacity is a question, right? So this looks like there is a gap. How do you get to capacity with irregular codes, with the LDPC codes? It turns out you have to optimize the degree distribution. Regular is not good enough. You have to optimize and get better degree distributions. And like I said, there are rate half codes whose threshold is 0.0045 dB away from capacity. It works quite well. Okay, so 0.04 dB from capacity. Okay, so that is what this slide shows. And here are some degree distributions just to compare with regular and irregular. Okay. So if you look at the first one that comes here, okay, it has a threshold of 0.919, okay, which is already better than the 3, 6 regular code. And look at the degrees. Okay. On the right degree we have just 6 and 7. Okay, there are only 2 different degrees. One of them is 6, the other is 7. Remember, in rho of x we put x power j minus 1, and lambda of x we put x power I minus 1. Okay, so the degree minus 1 is what you put in the of x. So 6 and 7, just 2 different degrees. And on the left hand side you have many more. You have 2, 3, 4 and 5. Just with a little bit of playing around, you have got already 0.919. Okay. And then you have other degrees, and WC 10 means, when I say this WC, this is the maximum left node degree. Okay, that is what this is. This is the maximum left node degree. WC is the maximum left node degree for the irregular codes. It is only 10. If you allow a degree, left node degree of 10, you already get 0.956, and that is quite close to 0.979. Okay, and these are fairly old distributions. Maybe today there are better distributions. People might have found better ones. Okay, I mean, if you have a program that keeps optimizing degree distributions, you can just let it run for a few months. I mean, how does it hurt? Let it keep on running. Every week you might get a new distribution. It gives you a better threshold. Okay, so just keep on doing it. It doesn't stop you from doing it. Okay, so the last one is a bit of theoretical interest, but things like this, the second one with maximum degree 10, these are really interesting degree distributions. Okay, so very simple, not too complex. You can easily construct them, right? And it gives you a very good threshold. Okay, so some technical details which are not so important. Okay, so like I said, there are several constructions. Most of the constructions are random. Okay, there are some algorithms, and we don't have time to look at those algorithms. You can do a search on the internet, and you will find lots of algorithms and ideas on how to optimize the random construction. Okay, you have a certain degree distribution, you respect that, and then on top of that, how do you assign the edges so that your BER curve is better? I mean, there are lots of research that was done, and people have some algorithms. In particular, there is an algorithm called ACE. Okay, so it's a very popular and successful algorithm which you can try to use. Okay, so there are other methods also. I'm not going to go into that. And okay, so let's just skip this. Okay, so that's it. I think let's just stop there with the slides. So are there any questions on how I got these curves? Okay, this kind of behavior. Okay. So for instance, the existence of such a threshold you can show theoretically. You can show theoretically that for this evolution process, it looks like a fancy evolution process, right? But there are some analysis that you can do even for these things. It's not really that difficult, but once you understand what the processes are, you can do some analysis. It's a little bit involved, but not too involved, and show that if the channel satisfies some conditions, a threshold like this will always exist. There will be a sharp point, there will be a sigma star, before which probability of error will go to 0 as L tends to infinity, and after which it will not go to 0. You can show that there will be a sharp point where it changes. Okay, so that is something you can show theoretically, and there is lots of other theoretical analysis possible for this process, but we do not have time to do any of those things in great detail. Okay. All right, if there are no more questions, we can try and see, and try to move on to the next topic. Okay. So before we move on to the next topic, maybe I can mention one last time one final tidbit of information. Maybe we will come back to this later also, but LDPC codes in the standards okay. So mostly I'm going to be, when I say standards, I'm going to be talking about wireless communication standards. Okay. Maybe satellite also. Okay. Okay. So there is something called the 802.16 E standard, which is also the WiMAX standard. Okay. This has LDPC codes. Okay. And this DVB, I believe DVB-S. Okay. DVB-S is digital video broadcast. Okay. DVB-S also has LDPC codes. So these two guys have LDPC codes. There are also others, for instance I believe the Wi-Fi also, the latest, I think 802.11n Wi-Fi, is it Wi-Fi 11n, I think, yeah, this also has LDPC codes. Okay. All these have LDPC codes specified. So the type of LDPC codes that these things have, I mean the theory is pretty much similar, I mean you need a good degree distribution, which is also should be a little bit decent to handle, I mean you can't say 8000 as one of the degrees, it's a little bit difficult to construct those kind of things. So usually the block length here is a few thousands. Okay, so it will start at around 700 or so and go all the way up to say 5K or so. Okay. So even another standard that has this is CCSDS, which is a space communication standard. Satellite and all, so these things have it. So the block length is in this range, maybe it goes up to 20K max, okay, nothing below that. Okay. So you can't have too large a degree. Most of these codes, this is length like this. Typical rates you will see are, it will start at half, it's very seldom that you go below half, 2 by 3, 3 by 4, 4 by 5, these are standard numbers. Okay, people like small rational numbers, these are standard numbers that you will see. Okay, so this is the sequence that most standards will follow, 1 by 2, 2 by 3, 3 by 4, 4 by 5, 5 by 6. Okay, outside of coding, when you talk to hardcore communication engineers, these are the numbers that they can easily understand. Okay, if you say 0.813, then they are confused about what to do. Because you see why, right? I mean, when you design a system, you have to worry about clock rate and how the coding rate affects the clock rate, etc. Right? So if you think about how these things work, okay, so you are going to have some message data rate which is going to be a constant. Okay, depending on how your channel changes, you might have to use a rate half code at some time or a rate 5 by 6 code. Okay, if your channel is very good, you are going to use a rate 5 by 6 code. If your channel is very bad, you are going to maybe use a rate half code. Okay, but for both cases, you want to keep the message rate the same. Okay, then what has to happen? Your symbol rate has to go up for the rate half code and it will have to go down for the rate 5 by 6 code. So you have to have different clocks and manage them, and you can't expect people to divide clock by 813 or something. It's difficult to divide. So these are easy things to do. So that's why people use these kind of numbers. So these are rates, and then the most of the codes are irregular. Okay, and the degree distribution is designed according to density evolution criteria. Okay, and the construction is usually what is called a protograph construction. Okay, so let me explain this protograph a little bit more in detail. Okay. So what they would do is they will have a degree distribution, maximum degree will be 10 or something for the left nodes, for the bit nodes it will be about 10, beyond 10 I have not seen too much. Okay, so it will be 10 or lesser than 10. Okay, maximum left degree 10, maybe even less than or equal to 10. Okay, much lesser than 10 also is possible. Okay. So in the construction they will use this idea of a protograph. Okay. So instead of constructing a large random matrix with putting ones arbitrarily wherever you want, what they would do is they would do it in 2 steps. They will construct a smaller matrix which is reasonably random, and then they will expand it to a larger matrix, and that expansion will be very regular. Okay. So I will tell you how that will work, and the motivation for this is to simplify the VLSI implementation. Okay. If you have to store a large matrix with a sparse ones, and if it is very large, I mean for length 5k and all, it is going to become a large matrix. Today VLSI you can do it, but not at low power. Okay. If you also want low power, why do you want low power? You always want low power, right. So it is always good, because wireless devices, these are going to be handhelds, maybe even otherwise, if it is not, if it is even in the base station, you might want to conserve power. Okay. Conserving power is a good thing today. Okay. So for all those reasons protographs are preferred, and of course you have to show that doing this is as good as constructing a random graph with the full matrix. Okay. So people show those results also. Okay. So the construction is they usually use this idea called ACE. Okay. I forget what the expansion is, also something to do with edges and all that. So ACE is a popular construction for constructing these kind of things. So it's something that's used. Okay. So what is the protograph? The basic idea is the following: you construct what's known as a base matrix. Okay. Suppose let's pick some numbers to make it specific, and then you'll see the generalization is not too hard. So maybe the base matrix for the rate half codes. Okay, I believe this is the WiMAX standard. This is what they use. The base matrix is a 12 by 24 matrix. Okay. So 12 by 24, very small, it can be stored very efficiently, but the base matrix will be dense, it will not be sparse. Okay. It is 12 by 24, and the base matrix will have 3 types of entries. Okay. So I will also fix some z which is called the expansion factor. In the WiMAX standard, z takes values like 32, 36, or actually 24, it starts at 24. 24 square is 768, no? Am I right? No, it's not correct. What is 576? Okay, so that's the smallest. 28. So on, it all goes all the way up to 96. Okay, in steps of 4. Okay, so for a fixed expansion factor, you will have a base matrix. For every expansion factor, you will have a base matrix. The base matrix will have 3 types of entries. Okay, some entries will be 0. Okay, some entries will be -1. Okay, some entries will be -1. I shouldn't say 0, doesn't matter. Some entries will be -1. Okay, other entries will be between 0 to z -1. Okay. Okay, so remember it's a 12 by 24 matrix. Some entries will be -1. Other entries will be 0 to z -1. Okay. This is the base matrix. When you expand, to get the expanded version, you replace -1 by a z by z all 0 matrix. And you replace I for I between 0 and z -1 by a z by z identity matrix column shifted I times. Okay, column shifted either to the right or the left. Okay, it depends on the standard. Some standards might want you to shift to the left, some standards might want you to shift to the right, but both are basically equivalent, right? Whether you shift to the left or right, if you do it enough times, it becomes the other shift. okay, so it does not matter. So, some shifted version of the identity matrix. Okay. So, you have a small 12 by 24 matrix which depending on the expansion factor is going to be blown up into a larger matrix. Okay. So, if you pick z equals 96, you are going to get block length of 2304. Okay. So, it is a fairly large matrix, but you started with a small base matrix which was 12 by 24. Okay. So, you can go all the way up to 2k with that. Okay. For different z you define a different base matrix and this is what you do. Okay. So, primary reason for this is VLSI complexity, when decreasing the complexity in the hardware implementation, which is good. So, for instance, if you think of actually a communication system in total, if you think of your cell phone, it has maybe just one chip, these days there are cell phones with one chip, okay, and in that one chip what fraction do you think will be signal processing software for communication? Any guesses? It is going to be very small, okay, believe me. All the signal processing that you do for communications, all your entire communication thing is probably going to be inside a small, maybe a centimeter by centimeter maximum, it can't be more than that, it will be even maybe even less than that. Okay. So, it is going to be a few millimeters by few millimeters in area, that is all you will get for communication algorithms. Everything else will be what? All applications, I mean that is what people want in the cell phone. Who wants communication? Communication should be free. You want applications, you want to be able to MP3 playing this, and for when you want to fancy all kinds of what, Facebook, Twitter, whatever, you want everything else in your cell phone, you do not want communication. Communication should be small, that is the entire idea, and advancements that becomes much smaller. So, within that millimeter by millimeter area, I mean few millimeters for few millimeters area, a maximum of 1 millimeter square will be given for the error correctable code. Okay. So, you will not get more than that. So, you are getting like a millimeter square kind of area, right. So, maybe it is a little bit more, I do not know, but it is really tiny, that is what I am trying to point out. Okay. In today's systems are evolving, you can't say I want a huge area for my error control code. Okay. So, nobody will pay you money for that, you want it, but you cannot make money. So, in that context it really helps to simplify the matrix specification, and the specification can take some area, chip area in terms of memory also can be significant. So, you have to decrease all that, and this is pretty useful for that. So, that is the main motivation for doing things like this. Okay. And a couple of other things I should point out when it comes to implementation. So, the encoder complexity, okay, is something that should trouble you now. Okay. So, because if you have something like Gaussian elimination, you are going to get now a dense matrix again. What is the point in simplifying and making your parity check matrix sparse when anyway you have to store a dense generator matrix. Okay. So, it turns out even there, because of the protograph structure, there are a lot of simplifications. Okay. So, the protograph structure is useful for various reasons, alright, and the performance is not bad at all. Okay. It does not suffer because of this regular structure, you get a good structure. Okay. So, that is one comment I wanted to make, and the other comment I wanted to make about soft decoders is this idea of a MinSum decoder. Okay. So, you will hear this a lot if you look at implementation. We looked at soft message passing decoding, so the soft message passing decoder I mean it's definitely an approximate decoder, it is not very accurate because of cycles and all that, right, but still if you look at it in terms of being some kind of an ideal decoder, as in soft message passing is one of the best things you can do in practice, you can't really do much better than that. It has good performance, but in terms of complexity there are a couple of problems in terms of implementation and complexity. There are two problems. Okay. So, one problem is the check node computation is intense. Okay. So, computation is complicated, right, it involves a lookup and then an adder, then another lookup, then you have to split the sign out. Okay. So, it can be implemented, it is not very bad in today's VLSI, but still it is complicated, maybe you want to simplify it and see if it can be simplified. The other problem is needs sigma square, right? Does it need sigma square or not? Yeah, first step needs sigma square, right? If you are processing LLR, you have to multiply by 2 by sigma square to get the log likelihood ratio from the received value R. Okay, so there are some, it's okay. I mean, one might say you can estimate sigma square at the receiver. How hard is it to estimate the noise variance? So you might be able to do that. There might be several ways of doing it, but on the other hand, there might be cases where you may not want to spend time estimating it, or maybe you can do without estimating it. Okay, who knows? There might be some methods of doing that. Okay, so both of these are solved by the MinSum decoder. Okay, so the MinSum approximation solves both of the above problems. Okay, without taking too much of a hit. With about a, okay, these are all just numbers, about a 0.5 dB loss. Okay, so compared to the soft message passing decoder, which you can implement with the exact sigma square, with the knowledge of sigma square, the MinSum decoder, which does not need sigma square, will suffer about a 0.5 dB loss. Okay, if 0.5 dB is not a big deal for you, so you might say I gain a lot by not estimating the noise variance. Maybe I will estimate it wrongly, who knows, I mean, let me not take that risk. I will simply take the MinSum decoder, and if once again, I mean, it again depends on how you construct your code, how you design your degree distribution, etc., and etc., and all those things are not very well studied, but people based on extensive simulations have found that if you take a pretty standard degree distribution and construct your code well, then the MinSum approximation will not hurt you by more than 0.5 dB or so. Particularly the WiMAX codes are pretty good with this. Okay, so MinSum decoder is good. Okay, so what is the basic idea in the MinSum decoder? The bit node computation is exactly the same. There is no change in the bit node computation. Okay, but except that in the first iteration, you will simply send Ri. Okay, you won't send the log likelihood ratio. Okay, so you will simply send Ri itself. Okay, so that is the first step. Iteration 1, Ri is sent instead of what? Li. Okay, so you do not need sigma square. Okay, bit nodes same as soft message passing. Okay. So what you do in the check nodes is, okay, so take a look at this check node computation. I will try and motivate how you do the approximation. Okay, so remember the u that you have in the check node is f of v1 plus f of v2 plus so on till f of v something, I do not know. So, v, let us say w r minus 1, right. This is the computation that you are doing. Okay, this is for the magnitude, of course. Okay, for the sign you have another computation going on in parallel. Okay, so if you look at the function f of x, it is log tan hyperbolic x by 2. Okay, so tan hyperbolic x by 2 near 0, if x is close to 0, it simply becomes equal to x. Okay, so it's almost linear in the close to x. Okay, so if x is very small, what will happen if you take log of it? Okay, remember it's all absolute value. Okay, after you take log, you make absolute value. Okay, it's all positive. Okay, so what will happen to log of a small number? It's going to become very big. Okay, on the other hand, if x is very large, tan hyperbolic x by 2 is going to go close to 1. Okay, and then when you take log of that, you are going to get 0. Okay, so in this computation, the smaller values dominate. In particular, the least value will have the largest component. Okay, so what you do is you make this approximation that this is the same as f of min of this guys. Okay, remember all this minimum is absolute value. Okay, we have to take absolute value everywhere. Okay, so you simply approximate the sum by f of the minimum of these things. All right, that is the idea. Okay, so the observation is this f of x tending to 0, f tending to 0, oh my goodness, something has happened. X tends to 0, f of x is large, and x is large means f of x is tending to 0. Okay. So, based on that you simply make this approximation, you take the minimum in absolute value of these things and do f of f of. So, what will happen when you do f of f of, remember f is its own inverse, you will simply get equal to minimum of V1, V2 through VWR minus 1. Okay. So, this is the MinSum approximation. Of course, the sign equation will carry on as before, there will be no change in the sign, but you do not need an f. Okay. So, you simply replace f of by simply the minimum. Okay. Okay. And there are some modifications here. It turns out minimum is a slightly bad approximation. So, people usually offset it by something. There is like a 0.75 that you multiply by, just like that. Okay. So, do not ask me why, you just do it, it works better than before. So, you do something like that, some offset is done usually to undo the effect of this min, but let me not go into that, but MinSum basically the idea is this. Okay. So, look at what will happen at the check node. There is a very easy computation that you can do. Okay. You have a check node, you have WR guys connected to this, and you are getting V1, V2 all the way to VWR. What you have to compute is basically two things. Okay. You have to compute the minimum and the second minimum. Okay. You just compute two things, compute the minimum and the second minimum. What is second minimum? The next least value. Okay. So, second minimum is basically, okay, I do not know why I did so much, is basically minimum of this after you have thrown away the least one. Okay, second minimum. And then what do you do? How do you pass back messages? Suppose V1 was minimum, suppose this is minimum, what will you do? You will send the second minimum back. Okay, this is all absolute value only. Okay, the signs you have to anyway take care of, signs will have to be computed again. Okay, and what will you send for everything else? Minimum. Okay, on the edge that you got the least value, you send the second least value, because you have to not consider that, right? The extrinsic is what you have to send. So, you send the second least value, on everything else you send the least value. Okay. So, it is a very easy computation that you can do at the check nodes if you are doing MinSum. Okay. Okay, so this is one implementation idea. Of course, offset MinSum is another idea. Okay, so many other ideas like this. So, another implementation idea that people usually use is to change the schedule. Okay. So, right now the schedule is usually, well, when I say schedule of message passing, messages go from bit node to check node, then you do processing at the check node, messages go back from check node to bit node, etc., etc. Okay. So, if you go back and remember a long time back when I introduced the MAP decoder, I said basically the ultimate MAP decoder can be thought of as dealing with parity check by parity check, right. And the approximation that is done in message passing decoders is you go from one parity check to the other depending on your neighborhood, and then what do? You do not account for the dependencies when you combine the information from different parity checks. Okay. So, now how you go from parity check to parity check is called the schedule, okay, and the message passing decoder specifies a certain schedule. Okay. So, there are ways to modify the schedule now. Okay. So, people have found through experiments that other schedules are better. Okay. Maybe you do not have to strictly follow the message passing schedules, particularly for protograph codes. If you design them carefully enough, there is a schedule, I am not able to recall the exact name right now. So, if forget the name that they give for this, but anyway, so there are other schedules that people use where they will process one subset of the rows first, okay, and then they will go to another subset of the rows, and then they will go to another and actually they will process one subset of the rows, update all the columns, do a column processing, and then they will go to another subset of the rows and update all the columns again, and then they will go to another subset of the rows and update all the columns again. They will repeat that as opposed to doing all the rows, all the columns, all the rows, all the columns. So they will use different schedules, and that turns out to provide better performance, and it is also simpler. Okay. So ideas like this are used, okay, and these things, there are lots of papers on this. You can search, if you do a Google search, you will find so many hits for LDPC implementations. Okay. So all these are practical ideas, and they have their value as well. Okay. When it comes to standards and implementation, you have to pay attention to that. Okay. Any questions on this MinSum idea? No, for instead of Li you will use R. Yeah, because once you go do minimum, scaling does not matter. See, the reason why you can drop the 2 by sigma square is whether I am scaling only in the beginning, right, even in the soft message passing decoder I am multiplying by Ri by 2 by sigma square, which is a positive number, and now if I only do minimums in the check node, I do not have to scale everything by 2 by sigma square. I can simply drop the scaling, any Ri is good enough. Okay. So I do not have to scale at all. So Ri itself can be used in the bit node, that is the idea. Because I am doing this f of and all that, I have to take care of the 2 by sigma square. If I do not do that, I am only doing minimum or some operation which does not involve any non-linearity in a different way, it is easy to just do Ri itself. So that is the main selling point also. Okay. Okay, so there is some 3 minutes left and we have to really make a big jump next. So let me just quickly summarize in this 3 minutes. Okay. So I think maybe it's a bit of a repetition here. So what we have been doing after the classical part, after the Reed-Solomon codes and all that, let me summarize that a little bit. We looked at optimal soft decoders. It is very interesting to me that the ML decoder does not have many approximations in practice that are implemented. Okay. The soft ML does not seem to have many approximations. I do not know why. I mean, it might be interesting to do that, because I will tell you why it might be interesting. Okay. But on the other hand, the bitwise MAP has several approximations. In particular, the nicest approximation is the message passing idea. Okay. And the design of LDPC codes beautifully feeds into this picture. Okay. So this is a kind of a big picture to remember. For a code, we saw that to get good coding gain, you have to do optimal soft decoding. Really, you can't do optimal soft decoding for large codes. When you increase k and n, you also have to increase k and n to get good coding gain. So when you increase k and n, you cannot do optimal soft decoding. But this bitwise MAP, particularly when you interpret it as going parity by parity with an approximation, seems to be a powerful idea, and message passing is a nice way of thinking about it, and LDPC codes are kind of made for this approximation. Okay. So you do that, you get a good implementation. Okay. So the problem here is, if you go to very low rates, rate like 1 by 10 or 1 by 8 or something, okay, then what happens is your parity check matrix really becomes large. Okay. And the bitwise MAP decoder, looking at parities, is much more inefficient than looking at the ML decoder directly. Right. What does the ML decoder do, the soft ML decoder? It does correlations with the code words only. If your code rate is very low, your number of code words is smaller. So maybe you should try and approximate ML, and to the best of my knowledge, I have not seen any ideas to approximate ML that. Okay. So in fact, so this naturally leads us to some other idea where the ML decoder might be very efficient. Okay. So is this efficient or not? Is there a code where ML decoder is really efficient? Okay. Turns out the answer is convolutional codes. Okay. So there are these codes called convolutional codes, where the code words themselves can be very easily described, so that the correlation between the code words can be done very efficiently, and your ML decoder becomes nice. Okay. And that is what we are going to see next, and that is a big jump, and it is very different from what we have been seeing now. So I will stop now, and tomorrow we will start with convolutional codes.